So today I'd like to talk about word embeddings for social science. And it's going to be an introductory talk, so I'm not assuming that you already know what word embeddings are. And my goal is to give you kind of a high-level idea of what word embeddings are, and to illustrate some potential of using them for social science, but perhaps also making you aware of some issues to think about. As mentioned, I work in the area of natural language processing. So I'm interested in automatically processing and analyzing natural language. And I'm particularly interested in text data, and text data is everywhere, right? We can think of text in news articles, we can think of conversations, online conversations, offline conversations, survey data, books, and so on. And all these data sources are a really interesting and rich resource, at least I think, to study societal phenomena. So to do this on a large scale, but also to sometimes find particular phenomena, analyze particular phenomena that actually are very rare, processing can really offer some exciting opportunities to do this. And a typical natural language processing system might look like this, right? We have some input text. This could be a document, or it could be a sentence or a paragraph or something else. We give it to this NLP system, and the outputs could be something like, well, what is the topic of the text? Or can we automatically generate a summary? Or can we automatically translate the text, and so on? And NLP has seen very large advances in the last few years. And one of the core components in most modern NLP systems are what's called word embeddings. And the idea is that it's really important to somehow capture or represent the meaning of words in our computational system, right? So for example, if you're building, let's say, a machine learning model, then somehow we need to encode the meaning of words in the model. And if we're able to do this, then we can ask questions like, well, how similar is cat to dog, for example, or how similar is Paris to London? Or if we aggregate it at the document level, how similar are, let's say, document A and document B? And these representations that somehow capture the meaning of words are used in many different ways. They are used for various natural language processing tasks like translation, classification, etc. And they're also increasingly used to explore social science questions. For example, how do people in different communities use language differently? Or how does the meaning of particular words change over time? And how does that relate to changes in society, for example? So we see that these word representations are also increasingly used in fields outside of NLP. So my goal today is to kind of introduce word embeddings to you, to give you some sense of what they are and how they are trained from the data. And then I'll give a high-level overview of two different applications or studies, one looking at societal biases and one looking at language change. So the first question is, well, how do we actually represent the meaning of words in our computational system? And some of you might think, well, perhaps we can use a dictionary for this, right? There are many dictionaries around. They are manually curated, tend to be very high quality. But the drawback is that dictionaries are quite hard to maintain. They take a lot of effort. And in practice, these dictionaries are often outdated, especially if we look at, let's say, domains like social media, or if we look at new words that emerge or new meanings that emerge. And they also tend to focus on, let's say, more general language use and might miss particular words or meanings that are really specific to a particular domain. So although in the past, many researchers did explore the use of dictionaries to incorporate them into natural language processing systems, nowadays, the dominant approach is to learn the meaning of words automatically from the data that we give to the system. And these representations of these words are done using vectors. So I'm not sure who of you are familiar with vectors. This is a very short summary. So vector is just a list of numbers. So here we see two vectors, A and B. So A contains two numbers, 5 and 5. And so that's why A is a two-dimensional vector. And if we have two-dimensional vectors, we can see them as points in a two-dimensional vector space, like what I show on the left. We can also have three-dimensional vectors, right? So for example, here, A is a three-dimensional vector because it contains three different numbers. And then we can see these three-dimensional vectors as points in a three-dimensional vector space. Now, the key idea in natural language processing is, well, can we represent words as vectors? So can we represent words as points in a vector space? So each point in the vector space would be a word, and words that have similar meanings would be closer to each other. So if we have good vector representations for words, then ideally, as I mentioned, similar words should be closer to each other in a vector space. And also, if we look at the relation between two vectors, so if we look at the positions of the words in a vector space, they should somehow reflect the relationship between these two words. Ideally, the vectors are also easy to use in a computational system. They should be efficient, which means, for example, that shorter vectors, so vectors with fewer dimensions, fewer numbers, are easy to work with. And ideally, they should also be interpretable, but this still remains quite an open question in natural language processing. So one way to test the quality of these vectors is comparing them with human judgments, right? So, for example, we could ask a group of people, like, how similar are smart and intelligent from a scale of 0 to 10? Or how similar are easy and big? Right, so, well, this was done in the past, asking a group of people. And for example, people said on average, smart and intelligent received a 9.2. They're quite similar. Well, easy and big, they are not very similar in meaning. And so on average, they got a 1.12. And we can imagine then correlating these human ratings with the distances between the vectors in the vector space. So we would want smart and intelligent to be close to each other in a vector space, because also we have a high human rating, and we would want easy and big to be farther away in the vector space. So how are these vector representations used? Well, they're used in neural networks like text classification, sequence tagging, and so on. And they're also increasingly used as research objects. So they're used for social science research, for research in linguistics, etc. So now let me describe a few ways that people created vector representations in the past, and then I will discuss the new approaches nowadays that are also referred to as word embeddings. So, that's a question. How do we get the point that easy and big are correlated as 1.2? That's a good question. So I probably wasn't super clear. So this was done by just giving these words to people and asking them to rate how similar they are. So 0 was not similar and 10 is very similar. And on average, people gave a 1.12. And then what we want to do is compare these scores that people gave with what the machine learning model has learned about these words. And if they correlate highly, then that's at least one way of saying, well, then the word representations reflect the meaning of the words well. Thanks for the question. I think that's a good to clarify. So the methods that I'm going to discuss are based on something that's called the distributional hypothesis. And that's the idea that we can often learn what a word means by looking at how it's used. Right? So, for example, here we see 3 sentences. And I actually have a question to you. What do you think the word wampos means based on looking at these 3 sentences? So feel free to put some thoughts in the chat, right? That's not like a clear wrong or good answer. But just by reading these 3 sentences, what's your impression of the word wampos? No idea. Well, I mean, yeah, some kind of animal, right? Yes. Anything more specific? Right? It could be an aquatic animal, maybe because of the scales, maybe. Yeah. Could also be a lizard. Yeah. Yeah, so thanks for the responses. I mean, of course, you don't know for sure just based on 3 sentences, but I think this already illustrates that just by having 3 sentences, you already get some impression of what it is, right? So I think most of you would say, well, it's probably an animal, and then you have some ideas of what kind of animal it could be. So actually, it's a pangolin. I just placed the words with a word that I made up. But you see actually that you were already thinking in the right direction, and you can imagine that if instead of 3 sentences, you might have had like 10 sentences or something, you would even have a more specific idea of what it means. So the distributional hypothesis is that words that occur in similar contexts tend to have similar meanings. So a lot of the methods that are used in natural language processing to learn the meaning of words are based on looking at the context in which these words occur. So this is one way of doing this, where we take as context the documents. So let's say we have 7 documents, and we just have 3 words. Right, so what we could do is just count how often each word occurs in each document. So let's say cat occurs 5 times in document 1 and 2 times in document 2. And dog occurs 7 times in document 1 and 3 times in document 2, and so on. Now, what we actually see is that in this way, we already create vectors for these words. So a vector representation for the word cat would in this case be 5201400. And words that tend to occur in similar documents would have vectors that are more similar to each other. Instead of documents, you can also use neighboring words. So in this case, you would count, for example, how often do the words cat and dog occur next to close to each other, or cat and car. And for example, cat occurs close to dog 3 times, right? So again, in this way, you again have vector representations for words. There are many different variants that you could use, right? So one question is, well, what do you take as context? You could use the words, the documents. If you take words, what window size, how many neighboring words do you want to use, and so on. And you can also think about, well, do you just want to take the raw frequency, so just count the words? Or do you want to apply some weighting or some normalization for length or something else? What we see in both approaches, though, is that these vectors are really big. So, for example, we often have tens of thousands, sometimes even 100,000 of documents, right? So each vector would have many different numbers, and actually many of them would be 0, because most words only occur in a small set of documents, or they only occur in occurrence with a small set of words compared to, let's say, the full vocabulary. So word embeddings are also these vector representations, but compared to what I just discussed, they tend to be shorter. So typically they only have about 50 to 1024 dimensions. right? So dimensions are just the number of numbers in a vector. But the nice thing is that they're very effective for many natural language processing tasks. Compared to what I just discussed, the vectors are dense. So most of their dimensions will have non-zero values, like I show on the slide. But the drawback is that these individual dimensions are less interpretable. So if we look at the word embedding for cat, for example, which is 0.52, 0.48, and so on, then it's difficult to say what 0.52 actually means, what the first number, what it represents. And that's because these different dimensions are learned from the data automatically, and therefore they are less interpretable, and which is still a big research question that people are trying to improve on. So now I'd like to discuss how we can actually learn these word embeddings from the data. So the idea is that we have some data set, like millions of tweets, or we have Wikipedia articles, or we have books. Then we give it to this learning algorithm, and then the output is going to be for each word, the word embedding. So for example, cat would be represented with 0.12 and so on, and then minus 0.2. And so the question is, what is inside the blue box? And there are different algorithms to do this. I'll just discuss one of them, word2vec, which is one of the most popular ones. So one of the key questions of learning these word embeddings from the data is, what kind of data can we use as a supervision signal? So what data can we use for the model to learn the meaning of words? And here the key idea is that actually we just need to have the text, and the text themselves can already act as training data for the model, and this is called self-supervision. So we don't need any additional manual annotation, for example. Right, to give you a concrete example, let's say we want to train a neural network to predict the next word in a sentence given previous words. You can imagine if you want to do this, the model needs to have some encodings or some associations regarding to language. It needs to encode some patterns in language. But you can create many of these examples just from your text data, right? If you have many documents, you can just remove some words in your documents and then ask the model to predict the missing words given the previous words. You don't need any additional labels or manual annotations. So here's one example that we could give to, let's say, neural network, right? We give words, and then we ask the neural network to predict the missing word. So for example, yesterday I went to the blank, or new study has highlighted the positive blank. And then the question is, which word comes next? So if we look at the first sentence, yesterday I went to the blank. A possible answer could be, yesterday I went to the park, or to the new store, or yesterday I went to the library. You see that, for example, location words are much more likely than some other words. You wouldn't really say, yesterday I went to the, or yesterday I went to the I, or something, right? So even if the model, even though it's impossible to always to always perfectly predict the missing words, a model that has some idea of how language works is able to do better than just randomly guessing a word. And if you give a model millions millions of these examples, then you can imagine that the model over time becomes better and better at predicting the missing words. So word2vec is a family of algorithms that's very popular and very influential. And it's very similar to what I just discussed, although the task setup is slightly different. So given a sentence, let's say the domestic cat is a small, typically furry carnivorous mammal, and we want to learn a word embedding for the word cat. So cat is then called the target word, and the neighboring words are called the context words. So here, the context words are words like the, domestic, is a, etc. And so you actually see that this really builds on this distributional hypothesis that I discussed before, right? Where we have a word and then we look at the context in which it's used. So Word2Vec was proposed in 2013 and has been very influential since then. And there are two different task setups that fall in the family of Word2Vec: the continuous back of word setup and the skipgram setup. Just here's an illustration. So with the continuous back of word setup, the idea is that you give the context words, you give the neighboring words, and then you ask the model to predict the target word, so the word in the middle. Skipgram is kind of the opposite, where you start with the target words, in this case they, and you actually ask the model to predict the context words. So I'll just discuss skipgram in slightly more detail because that one is used more, although both of them are quite effective in practice. So let's say that we have this sentence again: the domestic cat is a small, typically furry carnivorous mammal. Then we need to create many examples for the model to learn from. So what we do is we create positive examples. So these are word pairs where we take the target word, in this case cat, and a word in its context. So in this case, something like small or furry, for example. And these word pairs get the label 1 because we see in the data that actually small indeed occurs as a context word of the word cat. Then we also create negative examples where, again, we take the target word cat, and then we just randomly select another word from a vocabulary. And this is called negative sampling, and in this case, the label is 0. So cat and car, well, car doesn't occur near cat, so the label is 0. And then actually what we do is just train a logistic regression model to distinguish between the positive and the negative examples. And then the resulting weights that we get are actually the embeddings. So the embeddings are essentially a byproduct because this is not a task that we're interested in practice to then use for some kind of application. But by giving this task to the model, we are able to learn these word embeddings that are then used for all kinds of other purposes. Are there any questions so far for this part? Okay, so then let me continue. So now I'd like to give some examples of what these word embeddings can do. So people got really excited. It's a question: what are the common software? Is this an R thing? Yeah, I have some references at the end of the presentation, but there's really good software in both R and Python. And because it's used so much, these libraries are quite accessible. Yeah, so I have some references at the end where you can either train your own word embeddings on your own data, but also for many of these models, they are already available online. So you can also just download models that have already been trained on data and then just use them for whatever you want to use them. So you can either use models that are already trained on a big data set that people put online, or you can train your own model on your own data. So, so to give you an example of what these word embeddings can do, well, people got really excited about these word embeddings because by just learning from large amounts of data without needing, for example, manual annotation, it turns out that these word embeddings learn interesting properties about language. So for example, here these are word embeddings from a method called GLOVE. And these word embeddings have many more dimensions, but we can also plot them or project them on a 2D plane. And here we see, for example, company and CEO words. And if we look at them in a 2D plot, we actually see that the company words occur on the left and the CEO words occur on the right. So that suggests that these word embeddings have learned or encoded the relation between company and CEO. Or if we look at the figure on the right, then we've also find that words like slow, slower, slowest, or strong, stronger, strongest, they follow a very similar structure. So that again suggests that these word embeddings have learned these linguistic relations and that these are encoded in word embeddings. The most famous example, perhaps, if you've already heard about word embeddings before, are these analogies. So word embeddings also encode properties like gender, occupational associations, etc. And sometimes we can then do these kind of vector arithmetics in a vector space. And surprisingly, in many cases, it works. So for example, we could take the word embedding for the word king. We subtract the word embedding for the word man, and we add the word embedding for the word woman. And what we get is a word embedding that's very close to the embedding of the word queen. Right, so here's an example. So let's say we just have these four words in a 2D vector space, but in practice, these vectors are much bigger. Right, and so we see that these vector representations encode, for example, gender information. And if we have this word embedding for king, which is at position 4 and 2, and we subtract the word embedding for man, 1 and 6, and then we add the word embedding for the word woman, then we end up at the position where the word queen is. And so this got people really excited by the fact that if we just learn from lots of data, and that somehow these relations are also encoded in these word embeddings. One thing that I like to highlight, which I think is an important decision to take when you're training these word embeddings, is to think about what kind of context do you want to use, right? So distributional hypothesis, again, is that words that occur in similar context tend to have similar meanings. And the key question is, of course, how then do we define a context? And in many cases, we just take the neighboring words, right? So here we take the neighboring words where we say the window is 1, so we just take one word to the left or one word to the right. But you can also say, well, let's say we increase the window to 2, or we take the whole sentence as the context. And what research has shown is that if you take smaller context, then these words tend to learn syntactic properties. And if you take larger context, then these words tend to learn semantic and topical properties. I can't see the time right now. So how am I doing on time? Just to get an intuition of if I need to speed up or.
It's 11:04. We're ending at 11:20, so 16 minutes.
Yeah. Okay. Thanks. Okay. Then I might reduce this section slightly, and then spend a few minutes also on the other study. So one thing that I'd like to highlight is that is biases in word embeddings. So we learn these word embeddings from the data, right? And we know that these word embeddings learn all kinds of properties about the words. So if we look at, for example, the words she, he, sister, and brother, and these are word embeddings trained on Twitter data. And then if we look at their position in the vector space, then you see that they are positioned in this way as I show on the left. So going from she to he is very similar as going from sister to brother. And so that suggests that these word embeddings encode some gender relations. However, if we then look at some other words like nurse and surgeon, we actually find a very similar pattern. Going from nurse to surgeon, it's very similar as going from sister to brother or she or he. And this is something that I think many people would be less happy with, because what it means to be a nurse or what it means to be a surgeon isn't dependent on gender, right? If you look in a dictionary, if you look at the definition of nurse or definition of surgeon, you wouldn't find anything about gender there. Of course, it might not be surprising to some extent that the models learned this, because at least in many places there are more female nurses and there are more male surgeons. But you can imagine that if these kinds of associations or information is encoded in these word embeddings, it could be problematic if they're used in applications, right? If you think of recommendation or screening of resumes or something else, then some of these biases could propagate into these applications and reinforce, let's say, biases that are already there in society. So there's been a lot of research on how to measure biases in word embeddings, and particularly gender bias. And this is to assess the current NLP models, to also investigate methods that try to reduce the bias. But to some extent, it actually also presents an opportunity for social science, because there are also many studies that have used the same methods to study, for example, how societal biases have changed over time by training word embeddings on different time periods and then tracking how the biases that are measured in these word embeddings change over time and how that might relate to changes in society. A key question that's quite difficult is that societal biases are abstract concepts that cannot be measured directly, but they have to be inferred from observational data. Right, so this is one approach that was published in 2017 by Saliskan et al., who used or built on the implicit association test. So the implicit association test is based on response times. It has been widely used, although of course there are also limitations. So here's just one of the setups that are part of the implicit association test. So you have a word like John, and then you have to categorize John into left or right. So on the left we see male names, on the right we see female names. And so in this case, John should be categorized into the left. We also see two other words, family and career. And the idea is that if, let's say, family is more associated with male names and career is more associated with female names, then it's easier to do the categorization than when family is more associated to female names and career is more associated with male names. Right? And so the implicit association test looks at response times, but researchers have used the same setup, the same kind of words, but then instead of response times, looking at something that's called the cosine similarity between the embeddings. So if you have these embeddings in a vector space, how similar are the embeddings? And that's used as instead of looking at response times. And what they found is that they were able to replicate well-known implicit association test findings based on this method. I'm just thinking, yeah, I'll just describe this quickly and then I will go to the next part. So this is a study that we did recently where we looked at the reliability of bias measurements, because there have been many methods that have been proposed to measure these biases in these word embeddings. And the study that we did, which was with Yupei Du and Qishan Fang, took kind of a step back and looked at these different methods that have been used, and in particular looking at the reliability of these bias measurements. So this should give you an impression of the general setup. So there are many different variants of how we can measure gender bias in word embeddings. But the general setup looks like this. We have target words. So these are words like poetry, literature, drama, and so on. And we have these gender base pairs. And these are word pairs that are gender specific, like man, woman, father, mother, etc. And then we also have some kind of scoring rule where we measure how similar is poetry to, let's say, words like man and father, and how similar is poetry to words like, let's say, woman and mother in the word embedding space. And if poetry is more associated with man and father than with woman and mother, for example, then it's taken as gender bias, that poetry is more biased towards men. And so you'll see that to then calculate gender bias, you actually need to make many different decisions, right? Like what kind of target words do we need to use? What kind of scoring rules do we need to use? How do we actually measure the similarity? Which words do we use as gender base pairs? And we even see, and this has been shown by many studies, that even if you have exactly the same data set and the same algorithm, the results might also still vary based on how the word embeddings were initialized. So there's a bit of a random component there as well. And so the final scores that you will get will depend on many different factors. So in the study, we built on measurement theory, where we looked at reliability, which is the extent to which a measure produces consistent results over a variety of measurement conditions, in which basically the same results should be obtained. So we looked at 3 different types of reliability tests. We test reliability, inter-rater consistency, and internal consistency, where we took these ideas from measurement theory and then applied them to measuring bias in word embeddings. Now, actually, I think I'll just skip this part and refer to the paper if you're interested, which is shown here. It was published this year at NLP. But the main takeaway of this is that on the one hand, word embeddings do provide an opportunity for social science to, for example, measure all kinds of biases in these word embeddings. But we should think more about the actual measurements that we have, and in particular about reliability, but also the validity of these measurements. And that's something that has been studied not as much as probably should have. So in this particular paper, we looked at reliability, but it would also be great to see more work in on validity. How many minutes do I have left? Sorry.
7.
Okay, great.
I think if you go over, we'll totally forgive you.
No, it's fine. I think this section is a bit shorter and contains some examples. So I'll just I like to give some examples from this particular study, but for the word embeddings and biases, there are a lot of references there that you can take a closer look at if you like. So this is a study looking at how language is changing over time, right? Because there are, well, we know that language is constantly changing due to different factors, and also the meaning of a particular word can change. So this is a vicar from a paper by Hamilton et al. In 2016, where they looked at close words in the embedding space of words. And for example, if you look at broadcast, in 1850, it was associated with words like seed, scatter, circulated, etc. And then it moved more towards media broadcasting, right? So broadcast, well, initially it was mostly used as broadcasting seeds. Now broadcasting is used to refer to like radio or broadcasting radio or television signals. So there's a lot of interest in studying how language is changing, both from a linguistic point of view, but also we know that linguistic change is heavily influenced by societal changes as well. So one way to automatically track how language is changing is using these word embeddings that I discussed. So if you have data, like documents from different time periods, then what you can do is for each time period, you train word embeddings. So here we just have 2 time periods, period 1 and period 2. And let's say we have the word broadcast. So what we could do is we could look at, well, where does the word broadcast appear in the embedding space in period 1? And where does it appear in period 2? And if we see that its position has shifted a lot between these 2 time periods, that is taken as a signal that the word has changed in meaning, or at least in how it's used in our data. And we can do this on a very large scale, and in this way identify, for example, which words have changed the most, or even just tracking very fine-grained patterns of changes. So one study that we did was looking at language change in social media. So there's been a lot of work on language change looking at decades and centuries. Our study just looked at 5.5 years of Twitter data on a month-by-month basis. So just to give you one example of a word that has changed is the word lit. You can think of lit as lighting up a Christmas tree or referring to literature. Nowadays, it's also acquired this meaning of exciting and awesome, right? And so you find all these different uses on in Twitter as well. So here are a couple of the patterns that we found in our Twitter data. So we had 5.5 years of Twitter data. That's the x-axis. And then the y-axis shows you the message changed based on these word embeddings. And on the right, we see the frequency of the words. And the green line indicates the point with the biggest change. So, for example, we have the word glow, and glow was used in many different ways in the beginning of our data. But then in August 2013, rapper Chief Keef, he released this video, Kodak Glow Up One Day, and glow acquired this meaning of an impressive personal transformation, for example, in style or demeanor. And we actually found that just based on the data, that the model identified the biggest change to be in July 2013, which matches the release of this particular video quite well. Another example is the word Vine, which is also ranked highly by our system. And Vine was this video hosting service that was launched in January 2013. But of course, it's also used, for example, in the context of grapevine, right? But again, if we look at the system, then the biggest change was identified in December 2012, which also matches quite closely when the video hosting service was actually launched. The final example that I'd like to give is a more recent study where we just used the same approach, but then we looked at how the meaning of emojis is changing over time. So this is one emoji that was highlighted by the system, which is the school emoji. So if we look at words that were close to the skull emoji in 2012, these were words like zombie, corpse, bury, undead, and so on. So here we see that the skull emoji was mostly used in a literal way. Starting from 2013, we see other words like LMAO, etc., occur more closely to the skull emoji. So we now see that's more used in a more figurative way than this literal meaning that was used in the beginning. Right, so you see that actually what I just discussed does not only apply to words, but we can also use it to apply to emoji or other elements. So this was actually what I wanted to discuss. I have some resources and I'm happy to share the slides with you later as well. So here are 2 papers, or a chapter and an article that are both quite accessible, at least more accessible, I think, than the original papers. Especially the first one is written for a general audience. And here, these are mostly Python implementations, but for R, there are also many implementations available to train your own word embeddings or to reuse existing ones. So that's it. So thanks for your attention. And if there's time for questions, I'm happy to answer them.
Thank you so much. And yes, I do realize people may have to filter out, but if you have questions, please do. Maggie.
Thank you so much for this wonderful presentation. I learned a lot from it, and I really feel like this should be probably twice as long as the assigned time. I'm really, like, I have a lot of things I couldn't understand, or it was too fast anyway. So I have a question in a general direction of this type of research, which is you were talking about there are a lot of things that we can only infer from the data that we collected. It's not like so what is really the general utility of this kind of tool? Is it to predict what's going to come next for each word, or is it to, like, by based on the data that we collected, we can sort of see the bias or some kind of pattern within the existing corpus or whatever?
Yeah, so predicting which word comes next or which word is missing is more like a task to allow the model to learn the meaning of words. But that's not the task that we're actually interested in. So once the model has seen many of these examples, we can then take that model and apply it for something else. So this could be something like studying societal biases or studying how language is changing over time. But these models are also used as kind of a starting model for all kinds of applications. So people will take this model that has been trained on lots of data and then use it as a core component for topic classification or translation or something else. So it's used in both kind of applications as well as kind of more these social science type questions.
So basically, for research purposes, people are generally interested in these two broader categories. One is the bias in the embedded, and then the other one is like the longitudinal change throughout the years. Are there any other utility of such a tool in research?
Yeah, so there are. So I think these are two directions that are quite popular, but there are many other directions as well.
There's one that we're looking at, which is impact evaluation, being able to measure changes in people's language around sense of self. So actually, I have questions about whether that's doable, but I know that a number of us who do a lot of impact evaluation are looking at the potential of word embeddings as part of the approach.
Mm-hmm. Yeah, that's very interesting. I also am involved in a study where we look at survey questions, where we look at the embeddings of survey questions, and we're interested in, can we use them to either predict what people might answer or look at the quality of survey questions and so on. Based on these word embeddings.
It seems like it might also be a way of being able to identify distinctions between groups. So, when you're talking about broad social media data, you have a massive collection of people from all over the world, but then of course you have many different subpopulations. So I'm guessing you can also then link this to tests to be able to differentiate mean understandings of things.
Certainly. So instead of just looking at like longitudinal changes, of course, we can also look at differences, in the same time period between different groups, right? So are words used in different ways, or do words have different associations between different communities online, for example, or between people from different groups?
Mm-hmm. So pattern studies within the current data.
Yeah, I think a lot of the work is kind of exploratory, focused on patterns. Although I've seen some work that's a bit more like actually testing hypotheses or looking at causal questions as well. But that's very much work in progress, I would say. Yeah.
Thanks.
Yeah.
Very interesting.
I'm wondering about minimal sizes of the data sets. And I don't know if it works by sort of word count or gigabyte, or like how much do you need?
Yeah, that's a good but also a difficult question. So I think it depends on how many unique words do you have, right? So if your vocabulary, the number of words for which you want to learn word embeddings is smaller, then you would probably need less data. So it also depends on how much variation or how many different types of words do you see. But what you usually see is that people apply some threshold. So they say, well, only learn word embeddings for words that occur at least 5 times or 10 times in the data. But usually if you want to learn a model from scratch, you would need to have thousands of documents. But what you do sometimes see is that people take a model that's already trained on, let's say, a general data set, and then they only update the model using a smaller data set that is specific to their domain that they're interested in. So that's another option, that you don't train it from scratch. You take a model that's already trained, and then you only adjust the model to your specific task or domain. And then you need less data than if you would just train it from scratch.
Yeah.
But it's hard to give a concrete number because it depends.
Right, of course. I think when we look at, again, we're sort of looking at this as a potential way of doing impact evaluation and figuring out, number of clients, how much journal entries, data through sort of video diaries, things like that. How much data they're actually collecting, and then is that going to be enough to be able to actually see changes in how they're doing self-description? So we have, we're at the very beginning of the process of even figuring out if this is viable.
So how large are the data sets that you work with?
Oh, you're asking me or Maggie?
Yeah, you, Alison.
So most of the programs that we're working with have 100 to 200 individuals a year going through the program. And then they're incredibly variable in how much they actually write, do some journal entries. And so the sense was, we'd have some bias built in by we would only be working with those that had a lot of material that they had written. So I don't know off the top of my head, how much that actually becomes.
Yeah. But I mean, individuals is already, it's already quite a lot, right? I mean, depending on how much they produce, but I know researchers who are already very happy if they have 100 individuals or sometimes even less. Yeah, so you also see some exciting research nowadays where they try to train models on data from individuals to really track differences between people or how people develop over time. So there are all kinds of different applications or variations on what I just discussed.
Are there researchers who are particularly focused on individual development over time using word embeddings that would be good for the reference? I don't mean this to be a problem solving session for my but this is helpful.
So I know of two. At the top of my head, I know 2 or 3 different research groups. So University of Michigan has some work on word embeddings for individuals. I don't know if they've looked over time, but they did some work on training models on individual data. there's also Maria Lea Carter in the United Kingdom who's interested in tracking individuals over time, and she's interested in learning, I think more broadly, just representations based on language of individuals over time. And yeah, there are a few other ones, but I just can't remember the specific details.
That's a great starting place. I'm sure I can find them from there. Thank you so much. I'll take any sort of last questions and then we'll finish up.
Oh,
go ahead, Meg.
Is that okay? It's a little over the time already.
Yeah, go ahead.
Yeah, so I have a very rudimentary question about how this tool was used. I remember you said in one of your papers you did survey about how people rate two words correlated with each other, like easy and big and those kind of things. But it is not actually used when you are doing the natural language processing part, right? You are only talking about the context and embedding and all that.
Yeah, so this was not research that I did, but it's a data set that's often used. So so there are quite a few data sets where they ask people to give these kind of ratings. And the idea is that these are used to then assess the quality of these word embeddings. So if we have, let's say, different models to train word embeddings, then how do we know which one is better than the other one?
Excellent. Yeah.
And of course, there are different ways of doing this, but one way that people do is then correlating distances in the word embedding space with ratings that people give. So if people say that smart and intelligent are very similar, then we would also want smart and intelligent to be close to each other in the embedding space.
So how are you going to absorb that data? Are you going to manually adjust the correlation?
So the first step is comparing, right? So correlating the ratings that people give with the similarity between these word embeddings in a space. So there are different methods that can take the word embedding for smart and the word embedding for intelligent, and then calculate a number, right? So the higher the number, let's say it goes from -1 to 1, the closer to 1, the more similar these two words are according to the model. Mm-hmm. And then we can correlate the scores of the model with the scores that people gave. And if that's high, then that's taken as evidence that the model has done a good job. So that's one way of evaluation. And then there are also some other ways, although I think that's still also work in progress, where you can then also adjust the model based on some knowledge that you have, like some external knowledge.
I see. Yeah.
Yeah.
Makes sense. Thanks.